Hi guys, welcome to my channel. In this video, I'm going to present the concepts of finite automata and regular expression, which are important topics in compiler design. During the compilation, the first phase is lexical analysis. Lexical analyzer reads the source code and identifies the different tokens such as keyword, identifier, operator, and constant. Finite automata and regular expression provide the foundation for building the lexical analyzer. Let's go in detail and let's see with the slides. The agenda of today's presentation: Introduction to Finite Automata, Basic Components of Finite Automata, Representation of Finite Automata, Example of Finite Automata, Types of Finite Automata, DFA versus NFA comparison, Regular Expression, Basic Regular Operators, Relationship between the regular expression and finite automata, applications, and finally we'll end up with summary. Let's go in detail. Why finite automata? Finite automata is a mathematical model used to recognize the pattern in input string. It consists of a finite number of states and transition between those states. In a compiler, the finite automata are mainly used in the lexical analysis phase to identify the tokens such as keyword, identifier, constant, operators, to recognize the token during the lexical analysis, and also processes the input symbol by symbol and accepts or reject the string. So for example, when the compiler reads a variable name like student1, the finite automata check whether it follows the identifier pattern. I hope you guys understood. Let's move on to the next slide. The components. The basic components of finite automata is like mathematically represented as FA equals Q sigma delta Q naught and F. Q represents the set of all the states available in the finite automata. Sigma represents the input alphabet which contains all the possible input signal. Delta represents the transition function which defines how the automata moves between the states. Q naught is the initial state. F is the final state or acceptance state. You can see the diagram. Finite automata is divided into the 5 states and all it is represented as Q, sigma, delta, Q naught and F state. Let's move on to the next slide. A representation of finite automata. Finite automata can be represented in the 3 different ways. One is state diagram, another one is transition table, another one is mathematical representation. A graphical representation using circle. Circle always represents the states. Arrows represents the transitions. Double circle is nothing but a final state. Transition table. It represents the state transition in tabular form. It shows the next state for each input symbol. Mathematical representation. It represents the automation using a formal tuple. For example, M equals Q comma sigma comma delta comma Q naught comma final state F. This representation helps us to design and analyze the automata easily. I hope you guys understood. We'll move to the next slide. Example of the finite automata. You can see the transition diagram, you can see the transition table, and Q0 is always a start and Q2 is a final state, and this is all the acceptance and rejection based on the input, and transition, which transfer from one state to another. Let's move on to the next slide. Types of finite automata. There are two major types of finite automata. One is deterministic finite automata, another one is non-deterministic finite automata. Deterministic finite automata, it's nothing but one transition, single input, no epsilon. Non-deterministic finite automata, multiple transition from the existing state, even a epsilon transition is allowed. So here you can see one example, strings ending with A. You can see Q0 is a initial state where Q1 is a final state. Only one transition with a single input is transferring from Q0 to Q1. Characteristic, exactly one transition for each input, no epsilon transition. Each input has only one transition from that state. I hope you guys understood. We'll move on to the next slide. Non-deterministic finite automata. Sometimes it has zero transition, one transition, and multiple transition. And it also allows the epsilon transition. You can see the diagram here, Q0, where it is sent to the Q1 to transition with a single input. You can on input A. I hope you guys understood. So deterministic finite automata, single transition on single input, where a non-deterministic finite automata has a multiple transition on the single input. I hope you guys understood. Let's move on to the next slide. DFA versus NFA. One transition per input. Multiple transition possible. NFA. DFA, no epsilon transition. NFA, epsilon transition possible. DFA, faster execution. NFA, easier construction. DFA, more states sometimes required. NFA, usually fewer states are required because each state has a ability to transfer more than one transition. So fewer states are required. Use it directly in implementation. DFA. NFA converted into DFA. You can see the small example here. Input equals A, Q0 to Q1. A is transmitted. Whereas in the NFA, you can see Q0 is transmitted to the Q1. Q0 again it is transmitted here to the Q2. I hope you guys understood. Let's move on to the next slide. A regular expression. What is the regular expression? A regular expression is a pattern. Regular expression is a pattern description used to represent a set of string. It provides a single way to define the structure of tokens. In compiler design, regular expressions are mainly used in lexical analysis to specify the tokens. We have patterns for string. You can see the example A star, A plus, A question mark, A by B. Keywords if, else, while, identifier or letters or digits. You can see the small picture over there. I hope you guys understood. Let's move on to the next slide. Relationship between the regular expression and the finite automata. A regular expression and the finite automata are closely related. A regular expression can be converted into a finite automata. You can see the diagram. A regular expression NFA, DFA, minimize DFA. In compiler design, you can see regular expression, finite automata, lexical analyzer, tokens. This is the relation. Let's move on to the applications. Applications. A regular expression is used in the lexical analysis for identifying the tokens. Token recognition also uses the finite automata. Syntax highlighting uses the finite automata. And for searching a specific word or a specific pattern, we'll use the regular expression. Spell checking will use the finite automata. I hope you guys understood. Let's move on to the next slide. Summary. Finite automata are the foundation of the lexical analysis. Finite automata recognizes the pattern. DFA, NFA recognizes the regular languages. Regular expression provides a simple way to describe those patterns. Together, they form the foundation of lexical analysis in the compiler design. So you can see one small diagram, regular expression, finite automata, lexical analyzer, and which recognizes the pattern. This is how it works. I hope you guys understood. If you have any doubt, please raise your doubts in the comment box so that I can respond. Thank you, one and all.